So, hello everybody, welcome to the second lecture of the course Drug Delivery Principles in Engineering. In the first lecture, we learned why the drug delivery is important, what are the different modes through which the drugs get distributed in through the body. So, some pharmacokinetics is what we learned. We are going to continue further into the pharmacokinetics and introduce some more terms, so that throughout this course these terms will be used and you are familiar with these terms and know what this means before we go further into the course. So, today we are going to talk about elimination. We had talked about drug distribution previously a bit. This lecture is going to be mostly about elimination. And so, how are the drugs eliminated from the body? So, there are few major mechanisms and minor mechanisms that are responsible for the clearance of the drug or elimination of the drug. By far the most major mechanism is the through the organ called kidney. As you might already be aware of, we secrete a lot of urine through which we clear lots of drugs through our body. So, the major organ responsible there is kidney, which is responsible for filtration, which is responsible for secretion, and which is actually also responsible for reabsorption, which basically means that if you have, let us say, a molecule that the body may require and it does end up making its way to the kidney will send it back into the circulatory system, so that we are not running out of those particular molecules. So, these can be proteins, these can be other important things that the body may need. So, again as I said, by far when we talk about elimination, kidney is the major organ responsible. The next major organ is the liver, and again as we discussed in the previous lecture about the first pass metabolism, liver is essentially the metabolic organ of the body, which basically means it contains lots and lots of enzymes, lots of contact with the drug in the plasma. So, what it does, it breaks the molecules down into several individual components, which unlike kidney does not directly eliminate it from the body, it will still have to go through the kidney to get eliminated completely from the body. But then let us say if a molecule is broken down into 3 different smaller fragments, the activity may get lost, and so that way the drug itself is eliminated and converted into some other format, and it is no longer active. So, that is why it is important to talk about liver when we are talking about elimination. So, these two are the major organs that are responsible, and again depending on the drug there might be some other organs as well depending on how the drug is interacting with the body, but in general these two are the major organs. Then we also have some minor organs that are responsible for elimination, and one of them is lungs. So, mostly the elimination of the lung is through exhalation. So, we take in oxygen, we are eliminating CO2 every time we breathe, we are also eliminating some of the water every time we breathe. So, there is some moisture in the air that we are exhaling out. So, if you let us say inject a gas into the lungs or a gas into the circulatory system, those gases will have to then diffuse through to the lungs to get eliminated from the body. And then there are other some minor very minor mechanisms, so that could include sweating. So, we eliminate lots and lots of ions and water when we are doing some physical activity or when we are sweating. Saliva is another way that we eliminate few of the enzymes as well as some of the drugs, and of course, very minor contribution in many different circumstances in mother's milk and things like that. So, let us talk about elimination by the kidney, since we said that this is going to be a major organism, a major organ through which the elimination is going to take place. And so, essentially this is kind of a small unit in the kidney, it is called Bowman's capsule, and what it is essentially in the red what we are seeing is lots and lots of blood vessels, very tiny capillaries called glomerular capillaries that interacts with the Bowman's capsule at a very close proximity, as you can see here. And because of this close proximity, there is exchange of fluid, there is exchange of nutrients, there is exchange of drugs at this interface. And so, the drugs can typically diffuse out from this area into the Bowman's capsule, which essentially then goes towards the urine and causes the elimination. So, this is essentially where all the filtration, all the secretion happens. And so, if I really zoom into this mechanism 1, then and here is a picture on the right which shows it. So, this is a zoomed in capillary taking blood cells through it, and also your drug of interest. At the interface you have some endothelial cells which also have their glycocalyx. Glycocalyx is nothing but these proteoglycans, these lots of glycosylated proteins that are there, and they form a very tight mesh network which essentially filters anything above 100 nanometer is not able to pass through these, and but anything lower than that can essentially diffuse and filter out through these glycocalyx network. Then we have a globular basement membrane through which about up to a maximum of 10 nanometer can pass through, and then we have podocytes which are the kidney cells, and they are spaced such that they act as filters, and anything below 10 nanometer can pass through, and again it depends on the state of the person, what age they are, if they have any disease, these gaps may change depending on that. But in general anything below 10 nanometer is typically considered to be cleared by the kidney. And so essentially what a takeaway we can take from this is that particles that are above 10 nanometer cannot be excreted by kidney. So let us say if we want to eliminate the kidney excretion, what we would want to do is to make particles that are more than 10 nanometer in size, and those particles will then be entrapped and will not be able to pass through the kidney. In terms of the actual mathematics of this, elimination can be of various different types. One is zero order elimination, so that means that there is a constant rate of elimination in respect of the plasma concentration. So now we are talking about that, let us say we have a certain plasma concentration C in serum of a drug, and we are talking about how fast it is going to be eliminated if we want to study that. And why it is important? It is important because let us say if we want to figure out at what dose we should give it to a patient, we need to know first of all at what dose is the drug therapeutic. Let us say for example a drug acts at 100 mg per ml and takes about 1 day for it to manifest its effect. So we would like that the drug should be present throughout the body at least 100 mg per ml for 1 day, and to know that we need to know that how much drug we should give, so that the levels of the drug should never fall below 100 mg per ml at least for a day. So that is why it is very important to know at what rate it is building up as well as eliminating from the body, and there are some kinetics that are defined, and so zero order is one of them. And so when we say zero order, it essentially means that it is a constant rate of elimination. So no matter what is the drug concentration in the serum, it will eliminate at a constant rate. Another one is a first order, which is typically seen most often than not, and what it essentially means is that the rate of elimination is proportional to the plasma concentration. So essentially more drug you have in the body, the faster the drug is going to get eliminated, and as the drug concentration is going to go down, the rate of elimination will also go down. So essentially saying that constant fraction of drug is eliminated per unit time rather than the constant amount. And then of course there can be several other types of kinetics. There can be a second order, a third order, but we are not going to go much detail into that. So if we are talking about first order, it can be mathematically expressed as rate of elimination is proportional to the amount that is present at that time. And so essentially you can take out the proportionality constant and say rate of elimination is equal to some rate constant multiplied by the amount. So that is for the first order, and we will come back to it. Let us talk about an example. So in this case we will take a very popular example, especially among young adults, which is a zero order elimination of ethanol. So ethanol, when we consume it, it is typically distributed in the total body water. So not only in the plasma, but everywhere in the body wherever the fluid is, and we discussed in the last class that typically 80 kg human will have somewhere around 50 liter of total body fluid that will circulate. So for a mild intoxication to happen through ethanol, we need to have a plasma concentration of 1 mg per ml, and when again as I said that ethanol is distributed throughout the total body water, it essentially means that the total concentration of the ethanol in the body should be close to about 1 mg per ml in all parts of the body including the plasma. So how much should be ingested so that we reach that concentration, or how much typically when a person injects or consumes that much does it go to 1 mg per ml. So as I said the total body water is about 50 liters, and so we need to consume about 50 grams. So if we consume about 50 grams, we are talking about 1 mg per ml total plasma concentration, which is essentially, if you consider the density of the ethanol, we are talking about 63 ml of pure ethanol. So, okay, so let us say a person does consume about 63 ml of pure ethanol, builds up the plasma immediately builds up the plasma concentration to be about 1 mg per ml, then what is the next thing is going to happen. So, I mean technically if we are speaking, we are talking about strong alcoholic drinks like rums and whiskies, they have about 40 to 50% of ethanol concentration. So, we are really talking about 130 ml of strong alcoholic drink. So, it's not too high of a thing that people do not drink that much. So, it easily can be built up to that amount. Now, from the studies we know that ethanol has a constant elimination rate. So, as I said, 0 order elimination rate of about 10 ml per hour. So, regardless of what is the concentration of the ethanol that is present in your serum, it will get eliminated at a constant rate of 10 ml per hour. So, how much should a person be drinking to be able to maintain a mild intoxication which is at 1 mg per ml, if we know that this is the elimination rate. So, I will give you guys a couple of moments to figure this out. So, remember we are saying that the elimination is 10 ml per minute 10 ml per hour, and mild intoxication rate is 1 mg per ml. So, in the plasma. So, how much should the person be drinking so as to maintain this 1 mg per ml concentration in the plasma? Okay, so it's a very simple answer to this. Essentially, we should be drinking at a rate which is equal to the elimination rate. So, if we keep drinking at 10 ml per hour, that would maintain a concentration of 1 mg per ml, and that is fairly easy because it is a 0 order elimination. So, of course, the answer is that we have to drink at the rate of 10 ml per hour of pure ethanol, which again that means 20 ml per hour of a strong drink which is about 50% in concentration with the ethanol. And so, that is really not a whole lot, we are talking about less than one small peg. So, it is very easy to maintain this intoxication level, and in fact, it is very easy to go above this if we continue to drink irresponsibly. So, so essentially a word of caution, if you drink too much, the drunkenness can lead to coma and eventually to death. So, drink responsibly, but that is a very classic example of a 0 order elimination with ethanol. Okay, let us talk about first order elimination. So, here we are going to define another term called clearance. So, what is clearance? Clearance is the volume of the plasma cleared of drug per unit time. So, essentially clearance can be expressed as rate of elimination divided by the plasma concentration. And then another term that we are going to define is half life of elimination, and so that is very widely used in drug delivery fields, and what it essentially means is the time it takes for the plasma concentration to decrease by half. So, if I have 1 mg per ml, how long will it take for a normal body to reduce it down to 0.5 mg per ml. And so, again this helps in telling us the time to reach a steady state concentration when you administer a drug, as well as time for plasma concentration to fall after dosing is stopped. Yeah, so let us take a quick example here to get the kinetics. So, as we said that in first order elimination, we are saying that the rate of elimination is proportional to the concentration in the plasma. So, if I say the concentration in the plasma is C, then rate of elimination is what? dC by dt, and if I say that dC by dt is proportional to the concentration of the drug, we get a profile like this, which essentially when you inject the drug, the plasma concentration goes up because let us say I inject the drug intramuscularly. So, the drug has to diffuse from the muscles, go into the blood vessel and build up the concentration there. So, this is kind of the absorption phase that you are seeing. So, essentially at this time there was, let us say, an IM injection, intramuscular injection that was done, and from this time to all the way up to here, the drug is building up in the IV intravenous, and at the same time it is also getting eliminated at some first order elimination because the concentration is increasing. But by this time we are saying that most of the drug that we injected intramuscularly has reached a plasma concentration, has reached into the plasma. So, there is really no more drug coming from the depot that we had created intramuscularly, and from that point we are saying that since the rate of elimination is proportional to the concentration. So, since the concentration is highest here, we have a rate that is very fast here, but as the drug concentration in the plasma is decreasing, what we find is that the rate is also becoming slower and slower for the elimination. So, we get a curve something like this and we have to express it mathematically. We are saying, so we have to express it mathematically, we are saying again that dC by dt is equal to minus k, since this is decreasing the concentration multiplied by the concentration, and if I have to integrate this, what I can do is I can separate out the variables. So, this will essentially become dC by C is equal to minus k times dt, and if I now integrate both sides, the concentration of course will be from time 0 to t, and concentration, let us say from the initial concentration of C naught to some concentration C at a time t. If we do this, we find that this gives an expression of Ct, that is the concentration of the time, concentration at time t in the plasma is equal to the initial concentration multiplied by the exponential decay with time with some sort of rate constant or the elimination constant in this case. So, if I take logs on both sides, I will essentially get log Ct is equal to log initial concentration C naught minus the rate constant multiplied by the time. So, if you look closely, what is this term? This term is a variable. So, let us say this is y is equal to, what is this term? This term is a constant because we had given a constant concentration initially. So, let us say a minus this we can consider as a slope. So, let us say m, and this of course is another variable t. So, this is, let us say this is x. So, this essentially gives us the equation of a straight line. So, what I am saying is if I plot this graph that I just plotted onto a log scale, we will essentially get a equation of a straight line, and that is what essentially is represented as this is essentially y is equal to b minus ax. So, that is what is represented here. So, if I plot this on a log scale, we essentially get, and when I say log scale, it is a semi log scale because the plasma concentration is plotted on a log scale and time is plotted on a normal axis. So, we will essentially get a first order elimination which will be a straight line for this particular graph. So, if you ever see a straight line for a drug elimination on a semi log scale, that means it is a first order kinetics, and this is the typical equation that is represented by it. So, again we had talked about half life before. So, if I have to express half life in some other terms, this is essentially elimination of drugs from the body usually follows the first order kinetics with a characteristic half life and a fractional rate constant. So, let us say we had defined already this rate constant as k elimination. So, what is clearance? Clearance is essentially can be tissue specific. So, we can say clearance in the body, that is in the whole body, or we can say clearance through organ. So, let us say through blood, or let us say through lungs. So, something like that. So, so it will depend on what is the rate and extent of the metabolism of the drug in that particular tissue. It will also be flow dependent. So, if a tissue is highly perfused, that means that the blood is going to constantly take it out. So, like kidney and liver have very high blood flow and have very high clearance, and again the total clearance from the body is the sum of the total clearance from all the organs. So, so rate of elimination, let us say, is equal to the rate constant k elimination multiplied by the amount in the body, and the rate of elimination is also, as we defined with clearance, is clearance multiplied by the plasma concentration. So, therefore, if you equate these two, you essentially get an expression of the t half, which expresses t half is equal to 0.693 multiplied by the Vd divided by the clearance rate. So, and remember what is Vd? Vd is the volume of the distribution that we discussed in the last class. Okay, so let us take another example. It is a very simple example. So, all we are interested at this point is to know how long will it take for the body to eliminate 100 milligram of drug X. And the assumption here is that the 100 milligram of the drug is in the plasma at time 0, and a value that we are giving you is that the drug half life is just 4 hours. So, I will give you guys another moment to kind of figure this out. It is a very simple thing. So, there are two ways to do this. One, you can do it empirically. You can say that okay, if the half life is 4 hours, so we can say that in 4 hours the drug concentration will reduce to 50 milligram. in 8 hours this is going to reduce by half again. So, this is going to become 25 milligram, and then we can further say that in 12 hours this is going to become 12.5. So, if we continue to do this, will eventually this value will continue to decrease, but remember this is not at this point, because it is always going to reduce by half, you will never have the drug eliminate completely, right, because this always continue to reduce to infinitesimally small value, but it will never be 0, but that is not what happens typically. So, if we do this, we say that about as is described here, continue to do this and we will have in 4 half lives we will have it down to 6.25. So, if we say that how much it takes for it to remove about 90% of the drug, it will take about 4 half lives to get it down to below 90%. And so, but then again when I said that it will never become 0, that is a theoretical case, but in actual cases it will become undetectable, because you have a certain measurement that we are using. Those concentration might be therapeutically not even viable, may not be even have any significance practically to have concentrations reduced to that low amount. So, typically all drugs do get eliminated in due time. Okay, so as I said, we are going to define few more terms, and these are terms again used quite a lot in medical fields as well as in the drug delivery areas. So, one is ED50, and what it means is the effective dose 50, and when we say that the drug has a ED50 of a certain value, that means that at that particular dose almost 50% of the population will manifest a given effect. So, again to give you an example, let us say if I have drug X and I say that it is used to reduce fever, and somebody is having a fever, then if I give the drug X to 100 people that are having fever, at the ED50 value of the drug, 50 of the people will have some sort of relief from the fever. So, that is called the effective dose 50, ED50. So, why is this important? Again, if I am a doctor, I am trying to prescribe something, I need to know what is the ED50 of the drug that I am prescribing. So, I need to prescribe higher dose than the ED50, because I want the patient to feel better. Another term we are talking about is TD50, which is essentially toxic dose 50. This is also very important. I do not want to give too much of a dose that it becomes toxic. So, again going back to the same example, if I am saying if I am giving a drug that has at a dose that is equal to the TD50 or greater than TD50, that means almost 50%, so 50 of the people will manifest a toxic effect. That could be vomiting, that could be, depending on the drug, that could have different toxic effects, but we do not want to really touch TD50. So, now if the doctor has to prescribe something, it will have to be between ED50 and TD50, because if it is more than TD50, then nearly half of the people will come back complaining about the toxicity, and if it is less than ED50, then people will not even benefit. So, ideally we want the drugs to have a very wide gap between ED50 and TD50, because if the gap is lower, then it is very hard for the doctors to prescribe the drug. And finally, the last thing in terms of these terms that we are going to talk about is the LD50, and then LD50 is essentially is the median lethal dose 50, which as the name suggests would mean that at this dose almost 50% of the subjects will actually die. So, that is something that doctors do not even want to come close to this. So, definitely is a no for the drug to reach this amount of concentration, but we do need to know what is the value, so that the prescribers have some sort of estimate as to what is the concentration they never want to reach. Okay. And so, the way we quantify the drug is through this method, which is essentially called a therapeutic index. So, a therapeutic index is nothing but a dose at which the TD50 or LD50 divided by the ED50. So, essentially if I say that the therapeutic index of the drug is high, that means that it has quite a lot high value of the ED50 and low value, and quite a lot of high value of LD50 and low value of the ED50. That means that the drug is good, because at a very low concentration you are getting some therapeutic effect, but the LD50 is high. So, you can essentially work in the regime in between the two to prevent any toxicity to the patient. Okay, so just an example here. So these are a typical curve that you will see. So you have on the y axis you have percent of individuals that are responding to the drug, and on the x axis you have concentration of the drug that was administered. So what you see typically is, let us say this is a drug that is used to induce hypnosis in patient, and so as the concentration of the drug is increasing, you will see that more and more patients are becoming hypnotic, which is what is the outcome that is desired for this particular drug. But then at a certain high concentration, in this case these are just some random values, it is represented that as the concentration of the drug is increasing further, it may eventually cause even death in people. So in this case the lethal dose 50 is right here, because 50% of the patient is dying at a concentration of about 400. So the therapeutic index of the drug is essentially 400 by 100, because this value is the ED50 and then this value is the LD50. So the therapeutic index comes out to be 4, which is actually quite low for the drugs that are typically used, because let us see, if we want 100% of the patients to respond, we may have few people dying, which is never desirable. Okay, so we will stop here. In the next class we will talk about some more things about TD50, LD50, and even talk about prodrugs and all. So we will see you next time. Thank you.